Welcome to the next lecture of the subject signal systems. We introduced the concept of linearity in this lecture and few other concepts for the systems. So right now we are talking about systems and not signals. Signals are the input to the systems, and system is a composition of subsystems or various components which are constituted in a meaningful manner to give the output. So the components must be joined together in a meaningful manner so that the output of the system has some meaning, right? So the systems can be categorized in terms of some properties. Some properties which are very relevant are linearity, time invariance, stability of the system, invertibility of the system, does the system has memory, or if the system is causal or not. So linear systems are systems which follow the principles of superposition and homogeneity. Superposition means addition basically. So if I apply two inputs to the system and I add the two inputs and then apply, the output that comes after addition of the signals should be equal to the addition of the outputs when the individual inputs were given to the system. If this is so, then we say that the system follows superposition. But it is not only superposition that is important. We also need another property to be followed for linearity, and that is homogeneity. Homogeneity is basically scaling of the input. So if the signal is presented at the input of the system, we scale the signal by an amplitude. Say I make the signal half, the output should also become half. If that is so, then we say that scaling, or which is also called homogeneity, is taking place, is validated. If in combination both superposition and homogeneity takes place, then we say that the system is linear, otherwise not. So let us illustrate this concept using one example. The denotation is like that. I will write xt, then an arrow, and then equal to yt. So arrow means that xt is given to yt. Xt is given to system and the output is yt. So this means that we have actually given at the input xt and the output is yt. Of course, for continuous time systems, for discrete time systems, xn is given and yn is measured, right? So it is for discrete time case. Just quickly we can just check how we apply this rule. So we formulate that arbitrarily it is a system which is yt is equal to mxt plus c. So it means that the output of the system is some constant multiplied by the input plus some constant. M and C are the constants. So what we can do, we can arbitrarily assume, and this will be the standard procedure for evaluating. So I will take x1 of t, I will apply at the input of the system, I will measure the y1 of t. So what is y1 of the t? From this equation, clearly in place of xt I can write x1 of t, isn't it? In place of x1 I can write just simply like that. I can also write that if I apply another input, suppose I apply x2 of t, so x2 of t will give me not equal to, so it will be applied at the input, and therefore it is applied to give me y2 of t. Y2 of t is equal to mx2 of t plus c, because I cannot change m and c, I can only play around with x and y. Now for proving linearity, we will assume that we apply the third signal x3 of t, but this third signal is basically the combination of the above two signals. So it is a times of x1 of t plus b times of x2 of t. So this is my third signal. Now x3 of t is a x1t plus b x2t. What happens when I apply x3 of t to the system? We will just check that. So we apply x3 of t to the system. We observe what is y3 of t. So from the system of equations, you can write it m times x3t plus c. But what is x3t? x3t is a x1 of t plus b x2 of t plus c. This is the y3 of t when I apply x3t, which is a superposition and homogeneous combination of x1 and x2. So it is x1 plus x2 and a scaling also applied. So a x1 plus b x2. So it's x3 is basically a linear combination of x1 and x2. So we have applied this. Now what we need to prove? We need to prove that y3t is equal to a times of y1t plus b times of y2t. Otherwise, the system will not be linear system. The system will be non-linear system. So it's very straightforward. I can just calculate what is a y1 of t plus b y2 of t, and I can just play around with that. So what is a y1 of t? It is a times of, what is y1? y1 is here. So I can write m x1 of t plus c plus b, now y2 is here. So b m x2 of t plus c, and I can also just mathematically slight things that we can do with these terms, and that will be that it is, I can take m as common, so I can write this as a x1 of t plus b x2 of t. Okay, so there is no doubt here. Now plus it will be the part of c. So part of c, if you can see, both a and b have multiplied, so I will write it a plus b, isn't it? I will write this. And now what we are intended to, we actually want to compare this equation with this equation and see whether these two are equal or not. So these two actually make me first equation. So first combination of first becomes second, and the third equation is from y3t. And just from looking at it, we can see that the coefficient of c here is 1. The coefficient of c in a linear combination of y1 and y2 becomes a plus b, and therefore we can now straightforwardly go and write that this y3 of t that we just calculated, and if I compare this with a times of y1t plus b times of y2t, these are not equal. So from the concept, if I have applied the superpositioned and homogeneous combination of inputs, the output does not validate superposition and homogeneity, and therefore the system is basically non-linear. You can just quickly go on and check if this system of equation is yt is equal to mxt, so there is no c, which means for this case c is equal to 0. This appears to be linear combination, which means that this system is linear. It is just multiplying the input by some constant, so it will be linear. This, however, comes out to be a non-linear system. So it's a very good example to see. It is not only for continuous time. The same concept goes to the discrete time domain as well. So we can just quickly verify for this also. Otherwise, it is for you to see. But I can apply x1 of n. I can measure y1 of n, which is equal to basically from this equation x1 square of n. Similarly, I can apply x2 of n. I can measure y2 of n, and this will be x2 square of n. I can choose another third input, which is basically from our concept a linear combination of the two inputs, and then I apply this and I measure y3. So what happens? I can apply x3 of n. I can now measure y3 of n. From the system of equation, it comes out to be x3 square of n, which is to say it will be a x1 of n plus b x2 of n whole square. What is the combination of y1 and y2, which is a y1 of n plus b y2 of n? What will be this? This will be a times of x1 square n plus b times of x2 square of n, and we can quite easily check that these two are not in agreement. So just compare y3t with the linear combination of the outputs in equation 1 and 2. So these two are not equal. If these two are not equal, the system yn is equal to x square n. So I can write that y3 of n does not become equal to a times of y1 n and b times of y2 n, and therefore the system is again non-linear. Now, just for general understanding, if there is any relationship which is squared, it's not linear. From basic elementary mathematics, we know this, that square combinations actually tend to be parabolic and therefore are not linear, and therefore the system which follows such kind of a relationship will not be linear as well, and therefore the system comes out to be non-linear. So this is the basics about linear systems. Now we go to the most important aspect, which is called time invariance. Time invariance means that if I apply xn to give an output yn, and if I shift the input by some value, so suppose I now apply x of n minus n0, n0 is any constant, and I measure y2 of n, and if y2 of n is equal to y1, or in this case you can write simply y of n, right, because I have not taken, so I can, if it is equal to y of n minus n0, then the system is time invariant. Otherwise, if not equal to y of n minus n0, then the system is basically time varying. So what, since it's in discrete time, the same concepts also apply to the continuous time, which I will illustrate in an example. Another terminology which is used is either I can write time varying, or I can write shift, because it's discrete time, so I can write shift variant, right, or shift invariant in this case. So the concept is basic, that I apply the input signal with a shifted version, I measure the output signal. If the output signal is also shifted by the same amount which the original signal will give me, then the system is time invariant. It does not change in time. That does not mean that the shifting does not produce a shifting. It means that the shifting produces the same amount of shift in the output. So the procedure for measuring this is very simple. I will take two signals. First will be, suppose, any arbitrary signal x1 of n. So I will take this signal, I will apply this to yield y1 of n, and from the system of equation you can just write it. It will be x1 square n minus 2. I can then take another new signal x2 of t, but this time this x2 of t is nothing else but a shifted version of the original signal x1 of n. So it will be x1 of n minus n naught. Now with this I will measure what is the output with x2. So it's just a two-step proof. So x2 of n when applied to the system yields y2 of n. What is y2 of n, by the way? It is basically x2 square n minus 2. But what is x2? From this part, what is x2? x2 is x1 n minus n naught. So I can replace x2 by x1 first of all, and n by n minus n naught. So this y2 of n, you can see, is x1 square n minus n naught minus 2. Just quickly look at this, you will appreciate what is taking place. So I have changed x2 by x1, I have changed n by n minus naught because of these relationships, correct? So just pay attention, and there is nothing which is tedious here. It's very easy. So I get y2 of n, which is equal to x1 square n minus n naught minus 2. What will be the shifted version of the original output? The original output means when the output was measured with input being the original signal. What is the original? The original is x1 of n. So y1 of n, if I take this and shift it with n naught, this will be in this equation, just replacing n by n minus n naught, it will become x1 square what n minus n naught minus 2. So again, from just 1 and 2, we can see that y2 of n is actually equal to y1 of n minus n naught. Means if the original signal was shifted by a given value, the output is also getting shifted by the same value, and therefore the system is time invariant. The system is time invariant. So I can write that this y2 of n is basically equal to y1 of n minus n naught. System is shift invariant, correct? You can verify that since it's a square, it will be non-linear system. So it's a non-linear system which is shift invariant. I can just give the same illustration for continuous time systems. For this system of equations, when yt is equal to t square x of t minus 1, I can just simply assume any signal x1 of t being applied and measuring the output y1 of t, which from this system of equation becomes t square x1 of t minus 1. I then apply x2 of t, which is basically what x1 of t minus, now this time I will use t naught because it's continuous time variable. I will apply x2 of t to yield y2 of t, which is basically from this equation t square x2 of t minus 1. But what is x2 of t? x2 of t is x1 t minus t naught. So I can simply write this as t square x1 t minus t naught minus 1. So this is my y2 of t. Now what is this y1 of t minus t naught? So in this expression, we can quickly write, in place of t, we'll write t minus t naught. So it will be t minus t naught square x1 of t minus t naught minus 1. We can now compare equation 1 and 2 and see that the two are not equal, because this is not being shifted here, this is being shifted here. So I can write that y2 of t is basically not equal to y1 of t minus t naught. Don't use the word shift here, use times. So I will write time invariant. The system is basically time invariant. The system will also be a linear system. You can see squaring is on the time, not the input. So therefore it is possible, it's for you to solve, but it is possible for the system to be linear. So it is always good to inspect the signal. The next big concept is the stability of the system, which is measured in this time as bounded input, bounded output, which means that when I apply an input signal which is bounded, the output should also be bounded. If it is so, then the system is stable. Just quickly looking at this example, suppose yt is equal to xt cos omega ct. If I assume that xt is bounded, what is the meaning of xt being bounded? Is that its amplitude is fixed. It is the xt is not tending to infinity. Tending to infinity does not mean in time. Tending to infinity means in amplitude, in y-axis. So the magnitude of xt is limited. So if that is the case, from this system of equations, since it is multiplied by cos omega ct, and we know that cos omega ct can be -1 and +1 at max, so the magnitude of cos omega ct is less than 1 always for any value of omega at ct, and therefore I can have xt into cos omega ct a finite value if xt is finite. The system is stable. Yt will be a bounded entity, and therefore system is stable. Like for this case, in this case, even if I say that xt is bounded, means that the amplitude of xt is bounded, but from this system of equations, yt is equal to t times xt, which means what? That t, as t tends to infinity, yt will also tend to infinity, irrespective of the amplitude of xt being a limited value, a finite value. System is unstable. Like for this system, this is k starting from -infinity to n x of k. So it is a summation of all the values of x taken at all values of k, and the final value of k is n. So just to retrospect, I can write that y of n is basically what? The summation starts at -infinity. Then there is x of say -1. Then I have x of 0. Then I have x of 1. And again, it goes like this. I have finally x of n. So x of n minus 1 plus x of n. So it is like this. You can understand, even if xn is a finite value, when I add it n times, and since it's a system which I can check till n tends to infinity, even a finite value added infinite times will give me infinity. So yn will not be bounded, yn will be unbounded. This is my conclusion. Yn will be unbounded. And please, again, unbounded or bounded does not correspond to the time, it corresponds to the amplitude. So yn is unbounded, system is unstable. Similarly for this, you can see that since there is n outside xn, even if xn is finite value, since we'll check the system till n tends to infinity. So n tends to infinity means yn tends to infinity. System again is unstable from the same concept that we have checked so far. Next concept is system having memory. So system will be said to be memory when the present output depends on the past inputs very easily. A system with memory is called a dynamic system. A system without memory is said to be an instantaneous system. So from this system of equations, just two of them like written here. This yn depends on past values, because it's addition from k starting from minus infinity to n, just we have seen in the 2 slides back, and therefore it will be a memory system, therefore it will be a dynamic system. However, in this we require future values but not the past values. At t we require t and t plus 1, so we don't require past values. The system is instantaneous system. It does not have any memory. Similarly for this, you can just quickly check, this is dynamic and this is instantaneous, correct? So like this we can just check whether the system is having memory or not. Last concept is the invertibility of the system. A system is said to be invertible if we apply the input xn, we measure yn, and when it is possible that this output is applied at the input of another system, and the output of this another system, if it becomes equal to the original input signal, then this system is said to be inverse of this system. So if this system is S1, this system is S2, S2 is the inverse of S1, vice versa is also true. So in this case, it's the basic concept. If I apply the input, measure the output, if I can apply the output of the system to the input of another system such that the output of this another system is equal to the original input, then the system is said to be invertible. So like this system, yt is equal to 2 of xt. It is very easy to see that what is happening, the output becomes twice of the input. So if I want the original input to be taken, I can just divide the output by 2, and therefore the system is invertible system. Just looking into it, if I have a system S1, I apply xt, I take out yt, which is equal to 2 times of xt, isn't it? So what I'm saying, I can apply this to another system S2, just for you to understand, and we can measure this wt. Now understand, if this S2 is such that that wt, so I can write S2 is such that wt is equal to half of the input. So what is the input? Input is 2 times of xt. You can understand that wt is equal to xt. So the output of the second system becomes the input of the first system. Therefore, S2 is the inverse of S1. It's very easy to understand. For this case, we can take system having yt is equal to x square t as equations. Can this system be invertible? For this, I always we tend to see that a square root is the operation that can make. So if I take x square and I take the square root, I will get xt back. But no, because a square root of 9 is basically plus minus 3. So the sign is missed in the operation of squaring, which means to say that square of both plus minus 3 are 9. And therefore in this system, even if I use a square root as an option to invert the system, the sign will be lost. Sign is important. Therefore I cannot get back the original signal. The system is non-invertible. Correct? The system is not inverting. We can also check it for this system. This is that we are adding all the past values to get the original value, just for you to understand and work. I can basically write this at k is equal to minus infinity to say n minus 1, and I can add x of k. Then this means that I am getting plus x of n minus 2 and plus x of n minus 1. And what does this mean? This means that I am keeping on adding. I am then getting x of n minus 1 and then finally adding with x of n. What is my purpose? My purpose is to take this xn back. So if these are two systems, you can just see, if I subtract this part from this part, I can get xn. So there is an inverse system using which I can calculate, get back the original input xn, and therefore this system is invertible. The system is invertible. Adds in more more and more examples are given to us, we will be always able to appreciate these facts. So with this, we come to the conclusion of this lecture, where we introduce the concepts of properties of systems, which are linearity, time invariance, memory based or not, and then invertibility of the system. Thank you.